Good afternoon, everybody. Thank you, Thaisa, and all the other local organizers for taking care of us. And well, today I will present the results that we have developed during the last years, mainly led by Silvia Tosi, who is a PhD student that is ending her PhD at the Observatory of Rome under the supervision of Paolo Ventura, Davika Kamat, and me. And she worked also together on this nice group of people. And well, what we do since a long time at the Observatory of Rome is to work with a cell evolution code that is called ATON. In the last 20 years, we were focused a lot on, they started later, but then focused a lot on AGB yields in terms of gas, firstly, but then we also coupled a schematic description for the dust production around these stars to compute dust yields. And then we applied these evolutionary tracks and knowledge about the dust production prediction to the study of many population of AGB population in several galaxies. But now, thanks to the effort mainly done by Paolo Ventura to extend the computation towards the post-AGB and planetary nebula phase, we said, well, let's start to see if we can learn something, also looking at these other objects, and if we can agree with what we understood in terms of evolution, chemistry, and also dust production from the previous phase, the AGB. So, well, I like to look at this transition in a way like a metamorphosis, because we have this embedded object that lose layers of kind of skin in terms of dust and gas that moves away. Then when they lose the last skin, appears the post-AGB, the kind of pupa, then quickly transform in a really nice, beautiful object with wonderful emissions and shapes. This is not actually a random choice of this butterfly. This is the Richmond birdwing butterfly, which is endemic here in Australia, can be found only in few places here. And this is to not only honor the great diversity of nature that we have seen yesterday, and we know that is present here in Australia, but also to remind that actually this transition is really fast, so we can apply this kind of study to few objects, but still we can learn a lot, because as has been said already by, for example, by Hans van Winkel from the day before yesterday, when we look at these stars, these are 3 examples of spectral energy distribution, we see that, well, firstly, as I said, the star is cool and is embedded by dust, so we cannot really see the central object clearly, but then the dust moves away, the star starts to warm up, so we can determine better the emission of the central object and the abundances. This is really crucial when you want to compare with models. And also, you still have a clear peak of the dust that is still present there. Then even more with the planetary nebula, well, you start to have a lot of emission lines to deal with, but you also see now also the gas. So it's really interesting. So, well, we started with looking at the post-AGB in the Magellan Cloud, and we also look at the Milky Way. And what we did is, okay, well, studying the spectral energy distribution, finding the post-AGB most studied and most observed, we can determine from this region of the spectral energy distribution the luminosity and the effective temperature, and then we're looking at the emission in the infrared, we can determine the chemical composition of the dust that is surrounding the stars, and for example, that we can determine the temperature of this dust, because cooler is the dust, further is emitting in wavelengths. And also you have a proxy of how much dust is present looking at the optical depth. In this talk, I will talk about tau 10, which is the optical depth at 10 micron. Then, when you have this parameter determines, you can compare with the evolutionary tracks that we have computed. Remember that for post-AGB stars, you have the iron determination, the carbon, nitrogen, oxygen, so many elements that helps you, firstly, to discriminate in terms of metallicity, so you can compare more easily with the evolutionary tracks, and then what we want to do is not only to have an agreement between the luminosity to assign a progenitor mass to these stars that we are observing, but also, of course, we must agree with what we predict with the chemical evolution, I mean, the surface chemical abundances that we expect at the end of the AGB, then that during the post-AGB doesn't change. So there must be this correlation, and this is what we were looking at, and we found it for this object. So, well, once we have an agreement in terms of the progenitor mass that we have for these objects, now we'll focus more on carbon stars. Sorry, but the oxygen-rich stars are really low mass, less interesting, way less interesting in this case. So let's focus on carbon stars, since it's carbon stars in this talk. And we are looking now at this plot where we have the luminosity, which is a proxy of the progenitor mass, because the luminosity it keeps constant during the AGB, the post-AGB. So in terms of the optical depth at 10 micron, so we are looking that more massive stars produce more, not produce, but still have more dust. And this is, in a way, an agreement with what we were expecting from the AGB phase. This is actually what we have seen also in the AGB observation, because higher is the mass, higher is the number of third JAP episode that is experienced by the stars, so you can produce more carbon dust starting from more carbon atoms. Well, also what we see is that we can look at them in terms of the distance of the dust layer, where is the dust now. And we have noticed that the more massive stars are the ones with the dust that is closer. And in a way, this is something that can be explained with the fact that more massive stars evolves more rapidly towards the transition. But, well, you also have to think about but when this dust was formed, actually, the last dust that we are looking at now. So let's make a kind of scheme to understand the methodology that we have applied, because we still can find some constraints. For example, if we consider one post-AGB, we are looking at it now here at this effective temperature. So the dust is at this distance, but when it was formed, it was closer to the stars, and the star was cooler, no? So this time cannot be too large. Otherwise, the time that the velocity of this dust layer to reach this position that we are observing now, since when it was formed, should be too low, too slow velocity. But then it cannot also not be too fast, this transition, because otherwise you are assuming that you form dust when the star is already too warm to have dust formation available around the star. So making this kind of comparison, and also comparing with the dust that you expect to form during the end of the AGB phase, we could understand that in most cases, the dust was formed immediately after this dusty layer that we are observing is formed immediately after the tip of the AGB phase, when the stars already start to contract. And this is something that can help us also to understand better which is the mass loss rate that occurs after the tip of the AGB. Because if we look here, we are expressing the time here starting from the tip of the AGB phase, and we plot different prescription for mass loss. This is the one that usually is used for carbon stars during the AGB phase. You see that if you apply such a prescription, you should spend too much time to reach the temperature that the star has now. So you need a steeper, a quicker mass loss, a steeper relation, and that the dust should be formed around 3000, 4000 Kelvin. So these are the kind of results that we have retrieved from post-AGB stars. But then we also try, well, let's see what we can learn from PNE if still we have information useful for us. This became a bit more complicated because we had to consider a wider spectral energy distribution, and I guarantee that is absolutely not easy to manage, because you pass from the UV to the infrared, and we wanted to shape the entire all the contribution in the planetary nebula. So we selected the sample of PNE that has the wider constraints, the wider number of constraints in the literatures in terms of the distance, the shape, the distance of the nebula from the stars, and all the chemical abundance available possible. And also, of course, we needed a spectrum in the UV, because it's useful to determine not only, for example, determine the carbon abundance in the gas of the nebula, but also to constrain the luminosity of the central star and the effective temperature. Then from the near infrared bands, you can constrain how much gas is still present around the nebula. And then from the infrared, you can determine the composition of the dust, how much dust is still present, and also the temperature of this dust. So, what we did is, again, to compare also with the chemical abundances, as I said, we use the oxygen as a proxy of the metallicity. In this case, you cannot use iron because it's depleted in the PNE. So even if you have the third eject that slightly increase the oxygen, still you can distinguish among different metallicity using oxygen. And then carbon, that is useful because, well, there is, a common knowledge that we have some uncertainties about the carbon dredge-up. I would say that is not that large and among different modeling. So in particular, in this range of masses between, let's say, 1 and 2 or 2.5 solar masses, there is an agreement about how much carbon dredge-up and how much carbon is at the end of the AGB phase. And so we can distinguish among different masses, comparing the carbon abundance if you have a good carbon determination. So once we have the luminosity, the effective temperature determined from the SCD, then you have also more constraints from the chemical abundances, then you compare this sample of PNE with your evolutionary tracks, and then compare them with the prediction from the dust production rate for a certain progenitor mass. What we see again is that there is a trend with the mass of the progenitor. There is still more dust around the PNE for more massive progenitors. But in this case, we add an information about the mass of the gas that is still present in the nebula. And looks like that the gas in the more massive ones have been already lost. There is also a matter of how warm, how hot are the central stars, because we see also that there is a strong, the fraction of dust that is present is heavily lower than what we expect for the same mass at the end of the AGB phase. So part of the dust, of course, has been ejected, but also some of the dust should be destroyed during the heating process. So this is something that is still under the study, but I hope that I've convinced you that these are not actually a random choice of SCD, because we could determine the progenitor mass of these objects. And so what we are looking at actually are three different objects that lie on the same evolutionary path for the same initial mass progenitor. And so this is something that looks like a spot of the history of this transition. So I leave here my conclusion, my take-home message, and thank you.
You've been talking about the carbon-rich stars because you mentioned that they were more massive and everything, but can you do something similar for oxygen-rich stars as well, or?
Well, since these are rare objects, you sample the lower end of the range of masses that pass through the AGB phase. So what you see for oxygen-rich stars are always the really low mass stars that has a low envelope, so they produce a really low amount of dust, and so they are I mean, also in terms of the nucleosynthesis, the chemical composition are less interesting. Anyway, you see some dust around, you have less resolution in terms of extrapolating many interesting trends or
yeah, not as exciting, I guess.
it's a matter of the sample.
Yeah, okay. Thank you. Yeah, Ursula.
Just very quickly, there could be an even more massive, let's say 3.5, that is oxygen rich again.
Yes.
Or it could even be that the upper ones could, I mean, you could return to the oxygen.
Yes, we have found, for example, one post-AGB was at the border, at the edge between the hot bottom burning stars and the ones that becomes carbon. But well, there are really a few, and since we, for example, you could find easily in the PNE, no, because there are more. But at the end, since for this first study, we wanted to have really a lot of constraints from the observation, we ended with a sample that in mass has a small range of masses. We didn't have in this sample more massive PNE. I mean, for sure there are, but for this kind of study, we really want to have a lot of constraints from the literature.